This video lesson concerns the design of a modular cellular layout which can be controlled by means of Polca. Before talking about the cell layout that can be supported by Polca, we will first list a number of different layouts. First, we have the process layout, in which machines are able to perform similar processes are located in the same room. This type of layout is also called a functional layout. Several companies that initially have a functional layout decide to rearrange the workflow into a cellular layout. Here, machines are grouped in cells, and each cell is responsible for the complete manufacturing of a part family. In fact, a number of mini-factories has been created. If cells do not have overlapping capabilities with respect to the complete manufacturing of parts, then the cellular layout has difficulties to cope with changes in the product mix. In order to overcome this, the company may decide for a dynamic layout where the layout can be reconfigured according to the demand mix. Another solution to cope with changes in the demand mix is to develop a fractal layout, where cells are designed such that part families can be produced in more than one cell. A completely different layout type is the so-called holonic layout, where machines are seemingly randomly distributed on the work floor. As manufacturing orders arrive, those machines are selected which have available capacity and are located in the same area, if possible. A slightly different concept, not mentioned here, is the virtual cellular layout, where periodically cells are created for planning and scheduling purposes, but where the company still has a functional layout. A Polca layout is basically a modular layout where dependent cells are created. Each cell is able to produce some of the operations needed for products. Cells are connected by means of the goods flow. In case of Polca, the interfaces between cells are coordinated by Polca cards, so the interfaces are standard, which makes the layout modular. Finally, one has to recognize that several companies do have a hybrid layout, so they have some independent, autonomous cells, plus probably a process layout of the remaining machines. In this video lesson, we will concentrate on the development of a modular layout. Let us first explain what Polca does and what the acronym stands for. Polca coordinates the order flow between the dependent cells. Polca is an acronym for Paired Cell Overlapping Loops of Cards Authorization. We will explain this further. First, we have cells. For instance, cells P3, S2, and A1. Note that each cell may contain a number of different machines. A certain production order may need these three cells. Next, there are loops which overlap two cells. So, we have two loops for the red order. In each loop, Polca cards are running. A Polca card is therefore linked to two cells. The availability of a Polca card means that it is okay to start a manufacturing task of an order which needs both cells. This also implies that two Polca cards are needed in case the processing in cell S2 is needed. Here it is important to understand that there may be more than one machine in a Polca cell. Part types may undergo more than one process here. Polca uses high-level MRP for loading the cells. Each cell has its own lead time. This lead time is equal for all products that undergo processes in the cell. Given the lead times and the demand, the number of minimal Polca cards in each loop can be calculated. So what makes a good Polca cell? Here you see an example of the flow. What determines the throughput time in this cell? In order to find the parameters of importance, we will use Kingman's equation for calculating the average waiting time. Let us take this cell as an example and suppose that machine type B is the bottleneck. In other words, it is the machine type with the heaviest load. Here you see Kingman's equation for determining the average queuing time before a particular machine. The queuing time depends on the variability, V, of arrivals and processing times. It also depends on the utilization of the bottleneck, U, and the number of servers or machines. Finally, the queuing time depends on the average time that a job needs at a bottleneck. The Kingman's equation is useful for making a rough estimation of the average queuing time in front of a machine. It is not a very precise formula, though. Here it is important to understand the various variables. Let us apply the formula to estimate the total queuing time needed in a cell consisting of more machines. The queuing time in a cell is the so-called white space in quick response manufacturing terms. It is the time of an average job in a cell in which a machine is not busy with the job. The quick response manufacturing philosophy demands a focus on reducing the white space. Here, we assume that all queuing time in a cell can be calculated by focusing on the bottleneck. In reality, queuing time will also exist on other machines. In case that these machines had to be visited earlier in the routings of jobs, then the queuing on these machines will dampen the variability of arrivals at the bottleneck machine and, therefore, reduce the queuing at the bottleneck. We now neglect this dampening effect and assume that all variability of job arrivals at the cell has to be dealt with by the bottleneck machine. Machines that have to be visited later than the bottleneck in the routing of jobs will not face waiting time. Overall, we assume that the variability of machining time at non-bottleneck machines is such that it does not cause queuing time. So let us focus on the bottleneck when calculating the total queuing time in a cell. A very important variable which has the impact on the queuing time in a machine is the queuing factor U divided by 1 minus U. For example, if the average utilization of a machine is 80% and the average machining time is 1 hour, then the queuing factor is 0.8 divided by 1 minus 0.8, and that equals 4. This means that the utilization determines the queuing time with a factor of 4. In case of one bottleneck machine and a negative exponential arrival and machining time, or a so-called MM1 queue, the queuing time will be 4 times the machining time, so 4 hours. Two other factors of importance are the variability of arrival times and processing times. If there is no variation, which means that each job arrives according to a standard interval and requires the same processing time, then C sub A and C sub E are 0 and there will be no queue. The variability factor in that case is 0. An example for this is a dentist who works on appointment and needs 20 minutes for each patient to check his or her teeth. In case of completely independent arrival of jobs, or negative exponentially distributed arrivals and independent processing times, then C sub A and C sub E are both 1, and the variability factor is 1. If there are more independent bottleneck machines in a cell, then this will have a positive effect on the queuing time. The probability that one of the machines is free increases with the number of machines. As an example, suppose you are in a supermarket and there is only one cashier, and the checkout lane is occupied 80% of the time. The probability then that the lane is free as you arrive equals 20%. If there are, for instance, 2 cash registers and the utilization of each is 80%, then the probability that one lane is free as you arrive is substantially higher than 20%. Using the formula, you can calculate that the U factor will be 4 in case of one machine with a utilization of 80%. In case of 2 equal bottleneck machines with a utilization of 80%, the U factor will be 1.8. So, the queuing time will be substantially lower. The figure shows what the queuing factors U are in case of 1 or 2 identical machines with different utilizations. Multiplying the V and U factors gives us the number of jobs that are waiting in the cell. This has to be multiplied with the average processing time, T, of jobs at a bottleneck machine in order to get the total queuing time, or white space. As can be seen in the formula, the higher the average processing time of the job at the bottleneck machine, the higher the queuing time. So, it helps to reduce batch sizes. Of course, this may have a negative impact on the utilization of the bottleneck. The setup time needed for batching will take time. So, there is a trade-off here. Here you see a summary of what Kingman's equation teaches us with respect to the white space in a manufacturing cell. This formula helps us to determine the throughput performance of a cell. So what are the key lessons from this lecture? Lesson 1. The bottleneck machine in a cell determines the total white space, or queuing time, in a cell. So, specify the bottleneck. Lesson 2. If the bottleneck machine is more than 70 to 80% utilized, then it is likely that the total queuing time of a cell will explode. Lesson 3. Long queuing time can be reduced substantially if we reduce the variability of inter-arrival times of jobs at the cells and the variability of processing times of jobs at the bottleneck machine. Lesson 4. If there are equal machines in the company, then it is profitable to position them in one cell, especially if these machines are bottleneck machines. Lesson 5. Long processing times may frustrate the queuing time in cells. Finally, it has to be noted that we just calculated the average white space in a cell. In order to calculate the average total throughput time of jobs, we have to add the total average processing time of jobs in the cell. Thank you for watching this video lesson about developing Polca cells in a high-variety, low-volume company. The goal of this lecture was to explain Kingman's equation and to show how this equation specifies important variables which determine the throughput times of jobs in a cell.